Okay guys, what's up? Today we're going to get back into talking a little bit more about matrices and how they relate to linear maps, how they work, get a little bit more feel for it. Hopefully everyone is reasonably familiar with matrices from past linear algebra courses, so I bet a lot of this will feel like review. All right, a little bit of notation. I started doing this at the beginning of last lecture and then I stopped myself since it made more sense to do it today. Here is a little bit of notation we'll adopt. We will write for A an m by n matrix. Oops. Let me make sure my pen is right. There we go. All right, we will write for A an m by n matrix. We will take a j comma dot, it's a dot right there, to denote the 1 by n matrix that's row j of A. That is, if I put a letter in one of them and a dot in the other, I mean just the vector, whether it's a row or a column, corresponding to fix that j, and the other one have it run through all the possible values. Similarly, I'll do a dot k to denote the m by 1 matrix, which is column k of A. All right, cool. So hopefully that's not too weird. Basically, normally you write like a jk to denote the jkth entry, but if instead of putting a k in the second thing I put a dot, I mean let the k range over all possible values. Or if I put a dot in the first one, I mean let the j range over all possible values. That makes sense. All right, cool. So here is why we're going to use this notation. First little result. So let's suppose that A is an m by n matrix and B is an n by p matrix. Then the jkth entry of AB is aj dot times b dot k. That is, going back up here, it is the jth row of A times the kth column of B. Okay, that is, and I think this is relatively clear to see once you do the proof, you can represent each entry of a matrix product as a product of a row and a column vector in usual sense, right? Just of matrices of a certain shape, a list-like looking matrix. So here's the idea. So by definition, that is by the way we defined matrix multiplication, I will write it this way. AB, let me make it super clear by putting parentheses even. ABJK is equal to, well, let's just write it out. It's going to be A J1 B1 K plus, and we'll keep going all the way down to the very end where we get A J N B N K. That is, the outside ones stay fixed and the inside ones are what we iterate through as we do our sum. Okay, cool. But notice now that this is just, and I will write it out really quick, AJ1, AJN, that long vector times this one, B1K, all the way down through BNK. That is, you go across this one and down the other one, multiplying as you go and summing the result. And hey, wouldn't you know it, this is just A, J, comma, dot, B, dot, comma, K. See why I'm using the dot notation? Everything in this row of A's here has the same J, and the dot is what's varying. So let me make that in a different color to make it super clear. See, the dot part varies while the J stays fixed. Similarly, over here, the dot part varies while the K stays fixed. See? All right, cool. So that's pretty much just the most procedural, straightforward little bit of manipulation, but you just got to write it out to see it. Kind of nice to see that every single entry of a matrix product is just a product of a row and a column vector. All right, neat, easy enough. So here's another way to see it. This is slightly, I would say, a very obvious corollary from this one, but this is slightly different and will help build to, I think, the most useful way for us to see these things. So let me jump back to using yellow, which I've realized looks a little bit better when I invert the note packet colors, so you can print them off without using a ton of black, since on the other side of the color wheel is a nice dark blue. So here, let's write the proof for this one. This one says, hey, suppose A is an n by n matrix and B is an n by p matrix, same as before. Then, remembering how this works, the kth column of AB, that is, I'm putting a dot in the row part, or in the first entry, which is the tells you which row you're in, right? That's what it's sort of confusing if you say it the wrong way, but this is like the row part. That first entry is the row part. So if I put a dot there, it means range over the rows, fix the column. So this is the kth column of the product AB. This is just A times the kth column of B. It's a dot right there as well. Okay, so saying it in words, column K of AB is A times column K of B. All right, let's prove it. So, by the previous, result, A, B, JK, AB of the jkth entry of AB is equal to A, J, comma dot, B, dot, comma K. So, I'm going to put a period right there. Hopefully that doesn't seem confusing with these dots flying around. So, A, B, and I hope this is pretty easy to see what's going to go on here. Let's just take that J and replace it with a dot. This is A dot, comma dot now, B dot, comma K. But if I range over both rows and columns, that's just A. That's all of it, right? Hey, how about that? Kind of cool. All right. Let's see what else we can do now that we've got some nice notation and some basic results about how breaking a matrix down into columns and rows lets us say things about its product. All right. So we just learned that the kth column of AB is A times the kth column of B. So let's prove this. If A is an n by n matrix and B is just a column vector, an n by 1 matrix, then AB is just B1 times the first column of A plus all the way down to Bn times the nth column of A. That is, AB is just a linear combination of the columns of A where the scalars are the entries in B. All right, this is kind of neat because it helps make clear what matrix multiplication is doing. If you take a matrix, you multiply it by a vector, what you're doing is you are making a linear combination of the columns of A. This ties in to what we've been doing so far and maybe makes clear why we would care about this. After all, so far what we've been doing in this class is looking at a lot of linear combinations and trying to say things about them. This was the idea of span. This is the idea of linear independence. This is pretty much the key concept we've got so far. I mean, it goes back to sums of subspaces, direct sums, all that stuff, basis, etc. So this will be important. Let's prove this. By the previous result, we know AB, the kth column of it, is A times B dot K. Okay, so this is what we just proved right down here. The kth column of AB is equal to A times column K of B. But going back up here, But if B is equal to the little b that we've got right here, which is an n by 1 matrix, we have a B is equal to, well, it's just going to be a B dot comma 1. It's only got one column anyway, right? So it's equal to the only column it has, which is just equal to A times B dot comma 1. This says, now writing it out, so I will write the columns of A here, A dot comma 1, all the way down to A dot comma, now A is m by n, m rows, n columns. Okay, cool. And then little b, oh, I guess I should make that a little b there. Sorry, guys. I want to stay consistent. Little b. Big B's, little b's. There we go. Which, just to be clear from this part right here, in case that's not clear at all, this is just AB, right? Okay, so here, if we write this out, this is B1 through Bn. Okay, and just go through it. Now go across and down. Hey, that's the statement we want to prove, isn't it? Nice. All right, fair enough. Very cool. So, what does this tell us? Well, what this says is that matrix multiplication, when you take a matrix and you multiply it by a vector, you get a linear combination of the columns of A. We can extend this to talking about matrix multiplication, where instead of B being an n by 1 matrix, it's instead like an n by p matrix. Okay, so matrix multiplication is just a linear combination of columns. Here we'll suppose that C is an m by c matrix and R is a c by n matrix. Then for any k between 1 and n, so k is between 1 and n, column k of CR is a linear combination of the columns of C, where the coefficients in this linear combination are from column k of R. Oh, okay, cool. And similarly, you can do the exact same thing for j between 1 and m. This says that row j of CR is a linear combination of the rows of C, or of R, where coefficients come from row j of C. Oh, okay, cool. So the kth column of CR is a linear combination of the columns of C, while the jth row of CR is a linear combination of the rows of R. So for rows, it's from the second matrix, and for columns, it's from the first. Does that make some sense? Try to think of it like that. Columns correspond to the first spot, rows to the second spot here. All right, cool. Let's see if we can prove this out. So it's not actually that bad. It feels like it's going to be complicated and we're going to have to do like a ton of indexing, but I claim it's not actually bad at all. So suppose that k is in 1 through n. Okay. Then column k of CR, i.e. CR, now we're going to range over rows while fixing the column to be k, is equal to a linear combo of, well, what is it going to be? The columns of C with coefficients coming from R dot comma K i.e., the kth column of R by the previous result. So why does this work? So going up here, if B is an n by 1 matrix, then AB is just a linear combination of the columns of A, where the coefficients come from this B vector right here. All right, now, if I look at this guy right here, and I get the kth column of CR, well, this is a linear combination of the columns of C with coefficients coming from the kth column of R. That is, if you just fix RK, and you write it like this, here, let me write it. So I'll do it the straightforward way. So I'll go C R dot K, to be clear that I'm only referring to that one right there. This is just equal to, using the previous result, I will write it as this. It is C, the same way I did it up here, dot 1 all the way through dot n. Okay. And then this is, I will write it as a R1K all the way down to RNK. I've omitted some commas right there. But you go across and you go down, and hey, wouldn't you know it, this is just R1K C dot 1 plus all the way down to RNK C dot N. Look, it's a linear combination of the columns of C, where the coefficients come from R, the kth column of R. But now, all we have to do to see that this actually works, and maybe this is easier to see if you want to go back to an even further longer ago result, is this one right here, which says that AB, that product, its jkth entry, is the jth row of A times the kth column of B. So, going back over here, we want to say something about the kth column of CR. The kth column of CR, well, that is just column K of CR ranging over all of the different rows. So, fix the column K here and range over all of those rows, and wouldn't you know it, you just have the entire matrix and then the next matrix. So entire matrix, then the next matrix. This is C. Here, let me make this slightly easier to see. I've maybe kind of shoved this in here. I might be belaboring the point. This is just, let me move this very slightly so I can make it a little bit easier to see what's going on. All right, this is just CR dot comma K. This is the kth column of CR. Hey, look, it's a linear combination of the columns of C with coefficients coming from the kth column of R. All right, cool. The second part has the same logic. You just do the exact same thing. Basically now just looking back to this theorem right here, and instead of letting J vary, now we let K vary. Okay, nothing too crazy. So, all right, we can view multiplication of a matrix by a vector as a linear combination of the columns of that matrix, where the coefficients come from the entries in the vector. Vectors are just n by 1 matrices here. And similarly, we can view the product of two matrices in the same way. It is just a bunch of linear combinations of the columns of the first one, where each column of the matrix you get out is a linear combination of the columns of the first one, and the coefficients come from the corresponding column of the second one. Nice. And you can similarly switch this around and look at it with rows and so on, but it's the exact same logic. So let's do a bit more with this. Okay, here's why we care about that last result. So the reason why we want to view matrix multiplication in terms of linear combinations is that it will let us talk about the rank of a matrix. So we will talk about some factorizations we can do for matrices and how this lets us talk about rank. First off, we should define what rank is. So suppose we've got an m by n matrix A with entries in a field, of course. So the column rank of A is the dimension of the span of the columns of A in f m comma 1, i.e., column rank A is equal to dim span A, using our notation, the columns of A, dot comma 1, all the way down to, I should put, so maybe I should make this have a little serif to hide it from the comma I'm going to put here to separate the various entries, A dot comma n. So the dimension of the span of the columns. Similarly, the row rank is the dimension of the span of the rows, now in f1 comma n instead of fm comma 1. All right, fair enough. So here's the idea. Let's do an example. Let's take, I just pulled this straight from the book. Let's take A to be this matrix right here, 4, 7, 1, 8, 3, 5, 2, 9. Okay, column rank of A is the dimension of the span of the columns. So first column right here, second column right there, third column right here. And I am belaboring the point, but hopefully that is really pretty clear. So what is this? The dimension of the span of this is what? Well, let's look at the first two. Are they multiples of each other? That is, can you multiply 4 by something to get 7? Sure you can. You can multiply it by 7 over 4. But if you multiply 3 by 7 over 4, you certainly do not get 5. So these guys are, the second one is not in the span of the first one. But hey, notice there's just two things in any one of these columns. The dimension of that space is 2. So if you think about m here being 2, f of 2 comma 1, the 2 by 1 matrices, we proved last time that has dimension 2 times 1, which is 2. And look, I found a list, a sublist of this list, that has 2 linearly independent vectors. We know that if you have a linearly independent list of the length of a basis, it is a basis. So this list contains a basis for f2 comma 1. Hence, the dimension of its span is the dimension of f2 comma 1. It's 2. Nice. Okay, similarly, row rank, take the dimension of the rows. Let me switch colors here. So this first one right here, 4, 7, 1, 8. Look at that, 4, 7, 1, 8. Then 3, 5, 2, 9. Look at that, 3, 5, 2, 9. So if I take the dimension of this, what am I going to get? Well, let's look at this first vector and the second vector. Is the second one a multiple of the first one? Well, I can definitely multiply 4 by something to get 3. I can multiply it by 3/4. But if I multiply 7 by 3/4, I get 21/4, which is certainly not equal to 5. So I have a linearly independent list of the length of a basis I have a linearly independent list of length 2. The dimension of the space it spans is going to be 2. It's not the length of a basis. Since this is a bigger dimensional space, it's not a 2-dimensional space. But I have a linearly independent list of length 2. It naturally spans the subspace that is the span of those elements of the list. So I have a linearly independent set that spans this subspace. I have a basis for that subspace. It is length 2, so the dimension of that subspace is 2. Cool. All right. You may be noticing that there's something going on here. The column rank of A and the row rank of A here, these seem to be the same. Is this always so? That's the next question we'll answer. So to get there, we'll want a little tiny bit of notation, something that you have probably seen before. We'll talk about the transpose. So the transpose of a matrix A, which I'll denote by A superscript small t, is the matrix where you switch rows and columns. So the kjth entry of the transpose of A is the jkth entry of A. So just switch the indices. All right, nothing too crazy. Here's a quick example. Like if I take 1, 2, 3, 4, and I transpose it, well, I'm just going to flip things. So the 1/1 entry stays the 1/1 entry. The 2/2 entry stays the 2/2 entry. But the entry in the 1, 2 place becomes the entry in the 2, 1 place. And the entry in the 2, 1 place becomes the entry in the 1, 2 place. Hey, look at that. You're just flipping across the diagonal. Hopefully everyone's seen this. It's not too crazy of a thing to do. Basically, it says, hey, just pretend you got confused about your indices. All right, let's use this idea of flipping a matrix across its diagonal, turning rows into columns and columns into rows, to try to talk about whether or not the dimension of the column space of a matrix is equal to the dimension of the row space of a matrix. That is, the dimension of the space spanned by its rows and the dimension of the space spanned by its columns. It'll make sense to take columns and turn them into rows and rows and turn them into columns to see if these things are going to be the same. So we'll use the transpose, since that's what that does. Notice that's the case if you don't see it. Look, 1, 3, 1, 3. I've turned a column into a row. 2, 4, 2, 4. I've done the same thing here. Ah, cool. I turn columns into rows and rows into columns. Let's see if the column rank and the row rank of a square matrix are always the same. Okay, so to get there, to prove that the row rank is equal to the column rank, we're going to use a little trick. Here's the idea. So we'll start with A, an m by n matrix, entries in a field, and we'll suppose its column rank is greater than or equal to 1. All right, so we're basically just supposing that A isn't the zero matrix. Then we're going to say that there is an m by C, an m by the rank of, or it's the column rank of A. There's a matrix that big, C, and a column rank of A by n matrix R, both with entries in the field as well, such that A is equal to CR. All right, maybe this seems a little bit weird. It is a factorization result, notice. It's saying, hey, look, I can express A as a product. I'm factoring it, but it's actually not too crazy. Okay, so here's the idea. So the list A dot comma 1 all the way down through A dot comma n of columns of A can be reduced to a basis of span A dot 1 all the way down to A dot n, i.e., a spanning list in a finite dimensional vector space can be reduced to a basis. Okay, we know this, we've proved this one before. So we can take the columns and reduce it to a basis. This basis has length dim span A dot 1 all the way down to A dot n, which is, by our definition, or by our assumptions in the statement of the theorem, that's the column rank. It's the dimension of the span of the columns. It's C. Okay. So, the C different columns that form this basis can be used to make a matrix. And now I'm going to be kind of, this is unfortunate. I'll have to try to do it this way. I'll call it C. Or I won't, maybe I won't draw with serifs since that looks super silly. C, big C. So this is a big C. Can be used to make a matrix C, which has these basis elements as its columns. This matrix is now, so all of its columns have length, well, we've got m rows, n columns in A, so each of these columns here has m entries in it. Okay, this matrix has, there is m by C, little c, since there's C columns. Since any column in A can be written as a linear combo of the columns of C, let R be the matrix. Let R be the matrix whose, I'm going to be I'm going to try to be clear about this, whose kth column is the coefficients such that the kth column of A dot k, is equal to, and I'll write it this way. I'll write it as R1k times C dot comma 1 plus all the way down to R CK C dot comma C, where the C here is the little c that is the dimension of the span of the columns of A, the number of columns in C. Okay, cool. So since you can express everything in the span of the columns of A as a linear combination of a basis for the span of the columns of A, and since we've taken C to have columns that are such a basis, I can express every column of A as a linear combination of the columns of C. Then A is equal to CR, since the kth column of A is equal to a linear combination of the columns of C, where the coefficients come from the kth column of R. We just went through and showed, this was 2 slides ago, that the kth column of CR is a linear combination of the columns of C with coefficients coming from the kth column of R. We just did the reverse trick, and we constructed C and R so that I could write every column of A as a linear combination of the columns of C, and the coefficients came from the right column of R. Oh, cool. We did it. We're done. So if you've got an m by n matrix, you can factor it into an m by c and a c by n matrix, where c is the dimension of the span of the columns of A. That is its column rank. All right, cool. I mean, as long as it spans something other than the trivial subspace that just has the 0 vector, you can do this. If that's the case, then C would be equal to 0, and we can't get a 0 by n matrix or an m by 0 matrix, right? Those would just be silly. So what are we going to do with this? Well, we're going to use it to show that an m by n matrix has column rank equal to its row rank. Let's prove this. All right, here's the gist. So to start it off, let's let little c denote the column rank of A. Okay, then let A equals CR be the factorization assured by the previous theorem. Okay, so A is CR, where C is an m by little c matrix, and R is a little c by n matrix. All right, cool. Nothing too crazy so far. So what are we going to do right here? Well, we're going to notice that every row of A is a linear combo of what? The rows of the second matrix here of R. So I will get rid of that there so it doesn't look confusing like I'm saying some special R bar or something. Linear combo of R's rows. So every row of A is the linear combo of R's rows, and the coefficients in this linear combo come from C's rows. Okay, cool. So we've got every row of A as a linear combo of R's rows. Nice. Okay. Since R has C rows, this says that the row rank of A is less than or equal to C, its column rank. Oh, okay. That's not too crazy. Now, do the same to the transpose of A. So from this first part, we got that the row rank of A is less than or equal to C, its column rank. So row rank less than or equal to column rank. Now let's do the same thing for A transpose. And note that, well, here's how I'll write it. Column rank of A, well, since the transpose just turns columns into rows, this is the row rank of A transpose. The rows of A transpose are just the columns of A flipped sideways. Okay, but the row rank of A transpose, doing the exact same logic, is less than or equal to its column rank. But hey, the column rank of A transpose is equal to row rank of A. So the column rank of A is less than or equal to the row rank of A. But hey, so we've shown that the column rank of A is, well, so first off, we've shown that the row rank of A is less than or equal to its column rank. So column rank of A is greater than or equal to row rank A. And we've shown that column rank A from this part is less than or equal to the row rank of A. Hence, they are equal. If A is less than or equal to B and A is greater than or equal to B, then A is equal to B. Nice. All right, so all we had to do was factor A into CR, where C has as many columns as the column rank of A, and R has as many rows as the column rank of A. This let us get that the row rank is less than or equal to the column rank. Then repeating this on the transpose, we got that the column rank is less than or equal to the row rank. So one thing is greater than or equal to the other thing, and the other thing is greater than or equal to the first thing. So they're equal. So we can just talk about the rank. We don't need to specify row or column rank. We can just say, hey, let's let the rank of a matrix A that has m rows and n columns be the column rank of A, or equivalently, the row rank, since they are equal. All right, we've got this new, nice invariant of a matrix. So that is, we have this number we can associate with a matrix. We found that when we had a number we could associate to a subspace, that is, its dimension, this let us do all sorts of nice things. It let us build all sorts of useful machinery. This will serve essentially the same purpose. The rank, which, if you notice, just is derived from the previous invariant we got for subspaces, that is, we got this thing called dimension that you can associate to a subspace. We are going to do exactly the same thing. We will basically inherit this on over to matrix world, and we will use this number we can associate to a matrix to do a lot of useful tricks. That is, we can say that things are not equal if they don't have the same number associated to them. We might not be able to say that they are equal if they do have the same number associated to them, but we can definitely say that they're not equal if they don't have that same number. So this will be a big and useful trick. This will be a very useful tool, a big tool for us. We'll deal with it more next time. I'll see you then.